So our first speaker today is Henning Krause from the University of Bielefeld, who is going to talk about local localizable representations of finite groups.
Yeah, thank you very much. It is a big pleasure and an honor to be back in at the CRM in Bella, even though it is only virtual, but it's nice to be back. Actually, on my first slide, you see a picture from 2015 when my collaborators and myself, we were joining a program there. And you see us sitting there in the audience of this lecture room, all of us. So I'm reporting actually on some joint work with Dave Benson. You see him there, Shrikant Iyengar and Yulia Pevtsova. So my topic today is the notion of dualizability in for representations of finite groups. And I want to study this concept sort of locally. So therefore, local dualizable representations of finite groups. And please, so this is a sort of hybrid talk. So I prepared some slides, but eventually I start writing, and feel always free to ask questions or interrupt. I'm not always looking at the chat, but otherwise just tell me. And for example, the first obvious question which may come up now, if you look at this picture, does Yulia Pevtsova also have a MacBook? And the answer to that question is yes, she does have one. But let's now go to the next slide here. So I want to mention right away that the inspiration for this actually comes from stable homotopy theory. I'm a representation theorist, but I always look at what the topologists are doing, and they have their sort of category of Kn local spectra, and where Kn refers to the nth Morava K theory. And in this context, for example, there is a nice memoir by Hovey and Strickland. They studied this notion of dualizable objects. And this is basically what we try to import now into our category of representations. So I'm looking at representations of finite groups. So G is always a finite group, but it can also be a finite group scheme. Yeah, so this is the theory works equally well for finite group schemes. And K is always a field of positive characteristic. And then we look at representations, and this means we look at the group algebra, which I denote by Kg. And we may recall that this is a self-injective algebra. We denote by this here, the group cohomology, so with coefficients in K, of course. So you can think of it as the Ext or Uneda algebra of the trivial representation. Yeah? So think of K as the trivial representation, and the corresponding Uneda algebra gives you the group cohomology. Well, it's one way of identifying the group cohomology. And there's a classical result telling you that this is a graded commutative Noetherian algebra. This goes back to Evans, Benkov, even Goulot. Yeah, so we look at representations. So to be more specific, modules of Kg modules over the group algebra. And we look at all modules, not just the finite dimensional ones, even though we have, of course, a particular interest in the finite dimensional ones. And because this is a self-injective algebra, as I mentioned, then if we pass to the stable module category, then we get a triangulated category. So stable means I just take the same objects, but quotient out the morphisms factoring through a projective or injective module. No? So this is the usual sort of approach in a representation theory, killing the projectives. And then we obtain actually a compactly generated triangulated category. And the compact objects identify with the finite dimensional modules. And we have also a tensor product. So we have a tensor product, a monoidal structure, which you obtain by taking the usual tensor product of vector spaces, because every KG module is a vector space. And then we take the diagonal action to make it into a KG module again. You can do the same with the function objects. So you think of them as K-linear morphisms and take again the diagonal action to make it into KG module. So to summarize this, we obtain a so-called tensor triangulated category. And this is, of course, a subject most of you have seen before. And the category we want to look at is the actually local p-local category for any prime ideal in the cohomology ring. Yeah. So in a sense, the stable module category is sort of stratified by prime ideals of the cohomology ring. And to be more precise, so we fix a prime which is different from the unique maximal ideals. So I always look at homogeneous prime ideals, and then there's a unique maximal one of positive degree elements, and anything which is different we consider here. And attached to this prime, there is a functor which we denote by gamma sub p, which is the local cohomology functor. Yeah? And you can think of it as tensoring with a specific module, and this is often called the Ricard idempotent module. So this approach was sort of introduced in joint work of Benson, Carlson, Ricard, and there's a particular paper by Jeremy Ricard where he studies these idempotent modules. Anyway, it is sort of a nice tensor functor, which is obtained by tensoring with this idempotent. It's an exact and idempotent functor. And what we obtain as image of that functor, so we denote here by the essential image of that functor, so the full subcategory of objects which are of this form, this turns out to be a minimal tensor ideal localizing subcategory. Yeah? So it's a localizing subcategory, it's tensor ideal, obviously, and we think of those representations as local, sort of concentrated at the prime P. Okay, so this is the setup basically for the talk. We want to understand this local category, and to be precise, we want to understand the tensor triangulated structure. So because it inherits a tensor product from the big stable module category. And more specifically, we want to look at dualizable objects. Yeah? And there's a sort of simple observation which we should make right at the beginning. If we look globally at the category of all KG modules, then there is no difference between dualizable objects and compact objects. Actually, I will give the definition of a dualizable object in a minute, but there is usually no difference, so people don't pay too much attention to sort of that notion of a dualizable object. But if one works locally, there is a difference. Yeah? So any compact object is dualizable, but the converse is not true. Simply the tensor unit turns out to be not compact in general. Yeah? So this is the problem I want to address. Yeah? So we want to understand the tensor triangulated structure of this local category. And I think one should think of these local categories as the building blocks of the whole category. Yeah? And of course, what one always does is to sort of try to understand the smaller building blocks if one has a big category, which typically is wild and difficult to understand. So here is the plan for the talk. So what to be a bit more sort of precise what I want to do, I want to say a few more words and actually give some examples about the difference between compact and dualizable objects. And in particular, I give you the definition, I owe you the definition. And then I want to look at this p-local p-torsion category, which I indicated already, this gamma p of the stable module category. And I will state sort of a theorem which identifies these dualizable objects. And I want also to make some comments about a more general result for tensor triangulated categories, because I know that many of you have an interest in TT geometry. And I prepared also a small example. So sort of the smallest interesting example is the Klein foregroup. Yeah? And I'm happy to sort of explain this phenomena using this example. And then I also make a little excursion to the derived category of a commutative algebra, because there is an analog of the main result for commutative algebra. Okay, so this is my plan. And now let me fix actually a little bit more of notation and terminology. So as I say here throughout, yeah, so we have a tensor triangulated category, a compactly generated tensor triangulated category, T. So the unit is denoted by this 1. And I recall that an object is compact if the representable functor, the covariant functor, preserves all coproducts or direct sums in this category. And compactly generated means that we have a set of compact generators for that category. And usually one denotes by T up to C the subcategory of compact objects. It is a 6 subcategory, yeah? And it is somehow sort of essentially small category, which sometimes one calls also small objects, compact or small. So we have the tensor product, but the tensor product also has an adjoint, which is the function object, usually called function object. And I use this notation here, this curly hom. It is formally, it is the right adjoint of the tensor functor, and this right adjoint exists because of Brown representability. Yeah? The tensor product preserves, sort of by assumption, the direct sums, and then we get actually a right adjoint. And if we take the function object into the tensor identity, we get what the topologist calls Benyer-Whitehead duality. Yeah, because, you know, I mean, an example for such a setup is the category of spectra, and then it is the usual Benyer-Whitehead duality. And an object is dualizable, and often now people call it rigid, and originally it was called strongly dualizable, but let me just briefly call it dualizable. If we have an isomorphism, basically we can compute the function object using the tensor product with the dual of X. Yeah? So this is the sort of property, the natural morphism in this direction, yeah, for any object X. And if this is an isomorphism, the object is dualizable. Yeah? And this is sort of a nice property to have, in particular if compact objects are dualizable and vice versa. Category is called often rigidly generated. And here is one lemma, which is not so difficult to prove, sort of an exercise. If the tensor unit is compact, yeah, so in many examples we have this, yeah, if the tensor unit is compact, then automatically any dualizable object is compact. Yeah? Then dualizable objects are compact. But in general, the converse is not true. Yeah? And even this assumption is not always satisfied. Yeah? So if we actually go into our sort of motivating example, these categories I was introducing before, yeah, here, in general, the tensor unit will not be compact. Yeah? So this is exactly the kind of problem I want to address. So now I have used up my prepared slide and will start writing, and I hope my writing is reasonable. And I will actually start with some examples. I thought it makes sense to say a few more words about dualizable versus compact. So our first example was the stable module category, which I introduced already. They're compact and dualizable coincide. Yeah? And this is not so difficult to show. And by the way, the HOM, so this HOM function object is just HOM over K. I think I mentioned that already before. The next example, which is nice and well behaved, is the derived category of a commutative ring. So a commutative ring. Also in this case, we know the dualizable and compact objects coincide, and the compact objects are the so-called perfect complexes, everything which is generated by the ring concentrated in degree 0. Compact equals dualizable. Okay, so now let's take now an example where this is not true anymore. Sort of the smallest example, or the, in a sense, easiest example I can think of. Let's take a commutative Noetherian for simplicity. And we take for T, we take the homotopy category of projective A modules. Yeah, so we take not as usual the derived category, but the category of complexes up to homotopy. Sort of homotopy category of projective A modules. And then this is again compactly generated. I mean, one can show that it is compactly generated. And what are the compact objects? Well, it's a bit tricky. We can actually identify the compact objects with the bounded derived category of finitely generated modules. So small mod means the category of finitely generated modules by taking a complex X to a projective resolution, and then we HOM into the ring. Yeah. So we take somehow the dual of that, of a projective resolution. So duals of projective resolutions of finitely generated modules, for instance, are compact. Yeah. And certainly the tensor unit is compact, but there's a little lemma. It's not difficult to show that actually the dualizable objects, are just what is generated by the 6 subcategory generated by A. Yeah? So basically perfect complexes, but inside that sort of potentially bigger category. It's not just a derived category. On the other hand, I have just shown you that the compact objects are sort of bigger. So if A is singular, so if A is singular, then we have, for example, a module, then there exists finitely generated module M of infinite projective dimension. Yeah. And if we take then this dual of the projective resolution, this is certainly not dualizable because it's not in sig A, because it's an infinite resolution. Yeah, so it's not dualizable. But it is compact. Yeah? Okay, so you have seen at least one example which tells you that something interesting happens. And let me now proceed with group representations back again. So let me talk a little bit about local cohomology. So basically, to understand this category gamma p of the stable module category. So let me denote by R the cohomology ring and by T the stable module category. We can think of more general compactly generated triangulated categories, but for the moment we have just this. And we write for X and Y in T, we use this notation, hom star XY, to take the graded homomorphisms, meaning all homs from X into some suspension of Y. Yeah? So this is becomes a graded R module. So this is now a graded R module. And for example, one way of seeing it is if you take R and the map into the graded endomorphism ring of an object X, then you just tensor with X, and sort of the tensor unit, any endomorphism of the tensor unit. So these are sort of the graded endomorphisms of the tensor unit K. They produce endomorphisms, and of course here the endomorphisms of X, graded endomorphisms, are acting, say, from the right, and also the graded endomorphisms of Y are acting on the left, and these actions are compatible. Yeah? So graded, it is a graded module via this or via the corresponding map into the graded endomorphisms of Y. Okay, and now we fix a prime ideal. And I said always homogeneous prime ideals. Then X is P local. So we want to define what it means that an object is P local if this induced homomorphism from hom CX to the localization. So I can, of course, localize this if this is an isomorphism. So if P localization is an isomorphism for all compact objects. For the compact objects, I want that the graded homomorphisms are p-local. And let me denote by T sub p the category of p-local objects. So the p-local objects form a nice triangulated subcategory inside T. And this functor admits left adjoint. There's a left adjoint. As usual, sort of if one localizes, so the localization, the left adjoint takes an object X and T to X sub P. Yeah. Okay, so this was about p-local objects. Now I'll talk briefly about p-torsion objects. Actually, when A is any ideal, of course homogeneous, then we say at an R module, M is a torsion if M localized at Q equals 0 for any ideal Q which is not containing A. Yeah? So that's one way of defining a torsion. You can also think of it as elements being annihilated by some power of A. Yeah? But this is a better definition in a sense, because it tells you that we get some nice subcategories if you look at the torsion objects. So X in T is a torsion if, again, the graded homomorphisms from any compact objects are a torsion. So is a torsion an a torsion R module. Yeah? And this is for all compact objects. Yeah? So we just look at the morphisms from compact objects. And we write here gamma V of A, so the variety of defined by A of T. This is the category of a torsion objects. X is a torsion. Yeah, so we have again a nice subcategory, and this functor has actually a right adjoint. Has a right adjoint, so that was here my definition. A torsion has right adjoint. And the right adjoint is usually denoted by gamma sub V of A of X. Yeah, so if we summarize now, we have a notion of p-local, we have a notion of p-torsion basically, yeah, and we combine those, and that gives us a category of p-local and p-torsion objects. Yeah, so gamma p, to combine this is the local cohomology functor. It takes an object X. First we p-localize, and then we take p-torsion. Yeah. And it means we combine a left adjoint and a right adjoint, and that causes sort of some trouble in a sense. In particular, we cannot control so well anymore what happens with the dualizable objects. Yeah? So in a sense, yeah, first we localize, go to the P local category, and so we have, that's sort of our left adjoint of the inclusion, and we have also this functor the gamma p of t, and this has a right adjoint. Yeah, so we combine the left adjoint and the right adjoint. Yeah, so here this was this functor, and this was gamma v p. So what are the compact objects? Well, the compact objects we can control pretty well. So if we look at this subcategory, gamma p of t, yeah, so we sort of intersect. If we are interested in the compact objects, we take the compact objects, sorry, we intersect the p-local p-torsion category with the compact objects in TP. No? Yeah, so we take sort of the p, this functor actually t, the localization takes compact objects to compact objects. This sort of behaves nicely with respect to compact objects. And inside this category of compacts, we just look at those which are also p-torsion. Yeah? This is what I mean here. And then we get the compact objects, the p-local p-torsion compact objects. So the problem, and I think this I mentioned before, the problem is now that gamma pk is not compact. So that is a tensor unit. The tensor unit in this category is not compact in general. So it's not compact except when p is a minimal prime. But this is, of course, rare. Yeah? So in general, this will not be compact. So what can we do? I think I'm now sort of ready to state sort of the answer to that problem if we want to identify now the dualizable object, because the point is that the tensor unit is certainly a dualizable object, but yeah, it is not compact. So here's a theorem. And this is, of course, as I mentioned, joined with Benson, Jenga, and Pevtsova. And we look at any object in this p-local p-torsion category, gamma p of t. Yeah? So p is a prime in the cohomology ring. So Proch means it's a non-maximal prime. The following are equivalent. So we want to characterize the dualizable objects. So the last property which I'm telling you is that an object is dualizable. The first is sort of a cohomological characterization. Namely, we look at the HOMs, the graded HOMs from compact objects. So this is a finite length RP module for every compact object C Yeah, so we are working in this p-local p-torsion category. Yeah? So this is our P local P torsion category. And so maybe I just should sort of remind you, yeah, it was the image of this P local P torsion functor, local cohomology functor. And if we take homomorphism from a compact object, we want that this is finite length over actually the localization of R. Yeah. So the next property. Hom, the graded hom into X is an Artinian module. Artinian RP module for every compact which is globally compact. Yeah, so you notice the difference between sort of globally compact and locally compact, or P locally compact. And the third property is that this is X is in this sixth subcategory generated by the image of the local cohomology functor applied to compact objects. Yeah? So remember, so we had this problem. Here we were looking at the tensor unit, and the tensor unit is not compact, but it's certainly dualizable. Yeah. So for instance, here we have the tensor unit. We take its we apply the local cohomology functor, and this is then dualizable, and we take basically everything which is generated from that. Mm-hmm. And the last condition, as I said, is that X is a dualizable object. A dualizable object in this P local P torsion category. So a consequence, a corollary, is that these objects form a nice category. So these, the dualizable objects, form of, yeah, gamma P. Well, I'm now more specific. Yeah, it's a stable module category of Kg. Yeah, they form a nice subcategory. They are closed under the tensor product, the function object, and Spanier-Whitehead duality. Moreover, it is a Kuhl-Schmidt category. This is a Kuhl-Schmidt category. So this means, so this follows from this cohomological characterization. It means that every object decomposes essentially uniquely into finitely many indecomposable objects with a local endomorphism ring. The Kuhl-Schmidt category consisting of so-called sigma pure injective modules. Kg modules. So some people care about purity, for instance, myself. So sigma pure injectivity is sort of a strong finiteness condition, and these modules are sigma pure injective. And this implies already some nice decomposition properties, but we get even finite decompositions into indecomposables. Are there any questions? I mean, I should have asked before about questions, because I want to make sure that this sort of main result makes sense to the audience. Yeah? So we have now achieved a characterization of the dualizable objects in sort of various terms. There are even more characterization, more sort of properties one can think of, but I'll try to keep it simple. And I want now to stress the difference between compact and dualizable again, and this is another remark. I think I said that before, that if the prime is minimal, then both notions coincide. So an object X is actually compact if and only if HOM, the graded HOM, has finite lengths, over RP for all objects which are globally compact. Yeah? So compare this with the second property. Here we had Artinian. Yeah, for dualizable we had Artinian. So in a sense we compare now finite lengths with Artinian. Yeah? So we take the same sort of graded homomorphism from compact objects, and you know, I mean, over a local ring, so R sub P is a local ring, Artinian and finite lengths coincide if and only if the ring is Artinian or if the prime P is minimal. Yeah? Thus, compact is the same as dualizable. Of course, it shows you that compact implies dualizable, yeah, because finite lengths implies Artinian, but the converse is in general not true. So compact equals dualizable in this category if and only if P is a minimal prime. Minimal with respect to inclusion. Prime. Because then finite lengths equals Artinian over the ring, over this localized ring R sub P. Yeah? So this is sort of a simple consequence, and it tells you exactly sort of the difference. Yeah? So what next? So there's some time left actually for an example. Yeah, if we actually, maybe I should also make a comment about the proof. So maybe that was the first remark, and then there's a second remark about the proof. Yeah. So the proof, it's sort of specific to the situation in a sense. Yeah. So what are the crucial ingredients? Let me explain this. So the proof uses the Gorenstein property, of this category T, the stable module category. Yeah, so of course you can think of such a result more generally if you have a compactly generated tensor triangulated category and a ring is acting on it, and there are many more such examples, then one can ask what is needed for such a result. Yeah? In general, it will not be true. Yeah? So what is needed? And for our proof, we use a Gorenstein property. We use also strong generation of the category of compacts. There is this notion of strong generation a la Rouquet or Bondal-Vandenberg. And so, for instance, in our situation, the simple modules form a set of strong generators for the stable module category. And then we can use a Brown representability result, Brown representability in the sense of Rouquet I mean, he showed that if one has strong generation, there's sort of this Brown representability for, say, an essentially small category with a ring acting. And this has been actually extended by Janina Letz. She's actually here at this meeting as a participant and a speaker later this week. So this Brown representability is used, and also if one wants sort of a general result, one can use some fact that actually the strong generation is preserved under completion. Completion preserves strong generation. So this is something which Greg Stevenson is contributing. It is work in progress. So the proof is not completely written up, but this is sort of one ingredient, which gives you sort of a general result for compactly generated triangulated category with a ring action. For the specific situation of a stable module category, we have also another proof, which is not depending on Greg Stevenson's sort of unpublished work. Good. So there's that much about the proof. And now maybe time for my little example, the client for group. If there are no further questions at this stage. So let's look at the client for group. So I have prepared some couple of slides for that. So I remind you what is the client for group. It's we're looking at characteristic 2, and we take this group Z2 cross Z2, and the group algebra is sort of an elementary abelian group. So the group algebra is of this form. So it's of course a commutative ring. And my way of thinking of it is as obtained from the Kronecker algebra, meaning that the Kronecker algebra is a covering. Yeah? So the Kronecker algebra is obtained as a path algebra of this quiver here. Yeah? So we have this quiver with 2 vertices and 2 arrows, and it is called Kronecker quiver because the representations of this quiver, meaning that we put vector spaces at each vertex, have been classified already by Kronecker. Yeah, so it is basically the classifications of pairs of linear maps. And if we have such a pair of linear maps, we get always automatically representation of the client for group by taking the direct sum of V and W, yeah, and let the generators act. These generators X and Y are acting here on the left and the right. Yeah? Okay, I think this is not so complicated, and it's one way of thinking about representations. And basically all the representations are obtained from this covering. Yeah? Anyway, so remind you, the group cohomology is polynomial ring into variables. So if we take proj, so the variables are, have degree 1. If we take proj, we just get the projective line. We have the generic point. So what is the corresponding representation? Well, actually, we want to understand this category, this p-local p-torsion subcategory. Yeah. So if for this prime, for the generic point, we look at the so-called generic representation, which is here we take the field of rational functions and we take the corresponding action by the identity or multiplication with t, and then we get sort of a 2-dimensional representation over the field of rational functions, and this basically gives you everything for the p-local p-torsion category in this, for this prime, the this minimal prime. It's a minimal prime. And so it's just the additive closure of this generic representation. Okay, and the other situation is we take a closed point. Yeah. And then, well, if we look at the representations of the Kronecker algebra, we get a so-called tube. Yeah? So for each prime, the indecomposable modules are parameterized by the natural numbers. And there are sort of natural inclusions and surjections between these, and gives sort of the Ausländerreiten structure, and the Ausländerreiten quiver is actually a tube. Yeah? So we have these indecomposable modules, and if we have this sort of think about this chain of inclusions, we can take the union, and this is a so-called Prüfer module. Yeah? So we define by MP infinity the sort of direct limit or the filtered co-limit, the union of these modules, these finite dimensional modules. So this happens sort of on the level of Kronecker representations, but with this sort of push down functor from here to here, we get also our representations which are sort of P local and P torsion. So to be precise, we were interested in the compact objects in this category, the P local P torsion category, and the compact objects are just the finite dimension modules. Yeah, the finite dimension modules which I get from these so-called regular representations. And I take the additive closure, meaning just sort of finite direct sums. That's it. Yeah? These are all the compacts. So it's a very sort of nice structure. It's a tube. Yeah? In the Ausländerreiten quiver, it's a tube. Also in the Ausländerreiten quiver of the stable module category, actually, not only for the Kronecker algebra. But now we learned if the prime is not minimal, there will be more dualizable objects. So the extra object which we obtain is this Prüfer module. Yeah, that's it. Yeah, because the structure of the tube is very sort of rigid in a sense. There is not much more we get, namely just this extra indecomposable. So the dualizable objects. So here, this notation, maybe I have not introduced any notation for this. Maybe I just write here dualizable. The dualizable objects is just the additive closure of all the finite dimension modules plus the Prüfer modules. Yeah? So if you think of this process from getting from compact objects to dualizable objects, one may think of it as some sort of completion. Yeah? And I think one should try to make this more precise, sort of in more generality. I mean, here it's very easy. I mean, this completion is just sort of this direct limit. But yeah, I think there are other ways to make it sort of this sort of more conceptual, this process of completion. Any questions about this example? So this is sort of the smallest example where sort of something happens. Then let me get back. And I promised you the commutative algebra result at the end. So because some of you care about commutative algebras. So there is an analog. So A is now a commutative Noetherian ring. And we take for T the derived category of A modules. Yeah. And then, we take P a prime ideal, and we then for X in this P local P torsion category are equivalent. yeah, so we have something similar. So maybe we start with dualizable. So X is dualizable. Dualizable in this category, gamma p t. Secondly, so the cohomological characterization is that the rank over the, here we have now residue objects. So the rank over the residue field of the cohomology of Kp tensor X is finite. And the third condition is basically similar to what we had before. X is actually the image isomorphic to the image under the local cohomology functor for some compact object C in the derived category. Yeah, so you should compare this. Maybe we compare this with this property here. X is in sig of, yeah, so we take the local cohomology of compact objects, globally compact objects. Here we have to take the sig closure. In this situation, there's no need to take sig closure. So this is automatic. And we can say even a bit more. We have here this rank condition. There is sort of an obvious question, what happens if the rank is 1? If the rank, this rank of the cohomology of residue field tensor X equals 1, then we know actually that X is isomorphic to some suspension, say gamma S of the gamma P of the identity. But the tensor identity is the ring A itself, of course, or some integer S. Yes, so this is the commutative algebra result, and it's of course it's also a theorem, also from this joint project with Benson, Inger, and Pevtsova. And unfortunately, the proof is different. Yeah? So it's not the same proof. We cannot just copy the proof from the other theorem, because the other theorem was using some assumption. I mentioned the Gorenstein property, strong generation, and so on. I mean, all this is something we don't have for a commutative Noetherian ring. So maybe we have to wait and to understand, to get eventually some sort of unified concept to explain these results. I think I'm done with my presentation, and I'm happy to answer your questions and listen to your comments. Thank you very much.
Questions?
Hi, Henning, it's Joachim. So this thing that the units are not compact, that you see a lot in functional analysis, where people get a lot of mileage out of approximate units, which are families that approximate the units more and more. Do you see any of this in this setting?
No, I have not thought about this. Functional analysis, do you mean these C-star algebras or other situations?
Yeah, or Dirac functions.
Yeah, I see. Mm-hmm. No, I have not looked at that. And is that already sort of a global phenomenon, that the compact, the unit is not compact? Mm-hmm. No, I have not looked at such examples, but of course I should. Maybe I have to ask Sven Ake Wegner. He's usually
compact. Is that translation? I mean, is there a category where they're in functional analysis where they're compact objects, or is it more sort of a vague analogy? Sort of with compact supports or something.
That's a question for Joachim.
Yeah.
Joachim, we don't hear you.
Can you hear me now?
Yes.
Yes.
No, I was thinking of categories, just the operator algebras themselves, just as an analogy.
Okay, so maybe I can learn more from you at some stage.
Any other questions?
I have a question. In the localization that you mentioned, is it smashing? I mean, I seem to have missed it. I think. Is it smashing?
Yeah, the p-localization is a smashing localization. Yes, yes. You obtain it by smashing with the image of the tensor unit. Yeah.
And I mean, the stable module category is like a module category over like this date spectrum. Do you have any sort of characterization of this subcategories in terms of some Morita theory kind of thing?
Yeah, I don't think the characterization will be much different. Yeah, because again, you have this action of the cohomology ring. I mean, if you think about this characterizations here, we have the cohomology ring acting, and we always look at this action from the p-localization. So this, I mean, this will survive, this characterization.
Questions?
Well, maybe I can. So what should be the? So you do this in some cases like commutative rings and stable module categories and things like that. I mean, do you like envision some overall framework where this would be, where you could sort of have an axiomatic approach?
Yes, I think I understand exactly what you mean, and we don't have a complete answer at this stage. Unfortunately, there is no preprint available where you can convince yourself that there are basically two proofs. Yeah, I mean, the one proof for in this setting for the stable module category uses this Gorenstein property. I mean, this you can formalize, and we use strong generation. All sort of works nicely in these compactly generated tensor triangulated categories. I think that is sort of nice, but it is a specific context after all. Yeah, and the other proof is, well, using these residue fields in the commutative algebra. So these are the two proofs we can offer, and maybe we have to wait for some other sort of more clever people to find sort of a more general context. Of course, I should mention that also in this KN local category, yeah, these KN local spectra, and the proofs are very involved sort of for these kind of results. They also use some sort of regularity or strong generation. There may be a common framework. Yeah, I think that's all I can offer at the moment.
Right.
More questions?